In this video, we're going to start looking at section 15 from the online textbook. And this topic's called eigenvalues and eigenvectors. And in general, in English, we don't tend to borrow too many words for technical notation. We tend to get our own and use that, which can make something that looks like eigenvalues and eigenvectors feel very strange, because this comes from German. And the eigen just means characteristic. So there's nothing deep going on here. It's just the roots historically of where this came from. But it can make it feel like this is something exotic and European. No, it's not. People around the world use eigenvectors and eigenvalues all the time. And in fact, they're very closely related to something you've already seen. Determinants, in some sense, are a characteristic of a matrix. If you have a matrix, the determinant gives you some essence of what that matrix does when interpreted as a transform. Remember, the determinants tell you if you have closed areas or volumes in 3D or hypervolumes, what scaling effect that matrix will have. And also the sign of the determinant gives you something about whether things are mirrored in some kind of context. So the determinant gives you characteristics of the transform. These new words, eigenvalues and eigenvectors, are similarly characteristics that we can associate with the matrix and specifically with its transform. So it's going to be very similar to determinants in terms of feel. Now to get there, consider the question. Out of all the square matrices representing transforms, what are the easiest to work with and understand their effects? In other words, what matrix can you just look at and go, oh yeah, I know what that does? Well, I left off one, which is the zero matrix. The zero matrix just wipes everything out. The more interesting one that actually transforms in some way would be the identity matrix. In 2x2 or R2 space, it's this matrix, and R3 to R3, it's this. And we can just look at these. The determinant for I and in any dimension is always going to be 1. And you can make an area argument for that, because remember, the identity matrix does not change any vector. You get the same vector back. And so you get the same region back, and so you'd have the same area when you're done if you treat the determinant as the scaling factor. In fact, let's capture that as well. The scaling effect is all vectors are scaled by 1. That's what the scaling effect is of this particular matrix. So that's the super easiest. Let's go one layer deeper, one layer more complex, and introduce diagonal matrices. So diagonal matrices are matrices that have zeros everywhere off the diagonal. At all off diagonal elements. And you can see that clearly, most clearly in the 3x3 case here. All of these values that are not down the diagonal, either above the diagonal or below it, are all zeros. Now, can we capture the scaling effect of this matrix? Absolutely. Let's consider what we get if we multiply, let's call this matrix here A, by the vector 1, 0, 0, the nice basis vector. Well, if we multiply that out, we're going to get 2, 0, we're going to get 2, 0, 0. This nice structure of just diagonal elements leads to a scaling of the basis vector 1, 0, 0 by 2. If we take A times 0, 1, 0 and A times 0, 0, 1, I bet you can predict by the pattern we just saw what that's going to lead to, but let's confirm. Multiplying by the second natural basis vector here, we're going to get -1. Well, in fact, we know this, right? Because the columns of A are the image of the basis vectors. So in fact, we know the transform of the last one's also going to be the third column here. But what we care about now is interpretation. Because of this nice simple shape, we get the scaling of each vector by some constant, by some nice scalar value. So scaling of 0, 0, 1 by 1/2. So we have these scaling factors, 2, -1, 1/2, that apply to different directions now. All right, let's summarize that with the determinant though. You can do this either by the calculation of the submatrix determinants, or you can do your own little lines here. What you're going to get is, at the end of the day, the product of the diagonal elements. In a 2x2, it'll be 2 times 3. And this 3 4x3 matrix, it'll be the product down the diagonal. Even for 4x4, as long as all the off-diagonal elements are 0, you can do your submatrix calculations and you're going to end up multiplying at the end of the day just down the diagonal itself. And that makes total sense from an area perspective, because if we're scaling one dimension by 2, another dimension by -1, another by 1/2, the net effect of a 3-dimensional space transform would be to combine those three as a product. So you're going to get a product of the diagonal elements as your area effect, error and mirroring effect, that's captured by the determinant. So we're going to scale individual vectors in different ways, and we can combine those together to get the determinant. All right, so that's great. We can understand, this is the point here, we can look at a matrix that is the identity matrix and know what it does. We can look at a diagonal matrix and just look at it and know what it does. It's going to transform certain vectors in certain very specific ways. What if we branch out though and grab a semi-arbitrary matrix like this one here, 3, 1, 0, 2. It's not going to be as simple as the transform for the diagonal matrices, but let's just try some vectors in here. So I just made up 4 vectors. I just want to see what happens. How do we transform any vector with a matrix? We just do matrix multiplication. So this will be 3 and 0. So that gives us 3, 0. This would give us, again, I'm walking my fingers on the page, you can't see it, 0, 1, and 2. This would give us 3 plus 1 is 4, and 2. This one would give us -3 plus 1 is -2, and 2. Okay, now we're going to be looking for patterns, and specifically, we're looking for this kind of pattern. Is there some vector that got scaled? And actually, it looks like this one was, because this is equal to 3 times what we started with. So A scaled the 1, 0 vector by 3. What did it do with the 0, 1 vector? Oh, I don't know what it did. It changed it, right? This vector was not scaled. Or not just scaled. It was rotated or shifted or something else. So there's no simple pattern. This vector here, same kind of thing. We had 1, 1, again, not just scaled. However, this -1, 1 vector, hey, that was what we started with, but just times times 2. So what we found here is that A scaled not one of the nice basis vectors, but it scaled the vector -1, 1 by 2. So A scaled any vector in this direction by 3, and A scaled any vector in this direction by 2. We can actually summarize that in the next page. I'm going to just copy them because we wrote them out so nicely. And this one here. And we can actually figure out from context here, in 2 directions, we have some scaling, and one of them scaled by 3, one of them scaled by 2. Guess what? The total net effect on an area then would be scaling by 6. Does that match our determinant? Absolutely. We can do the determinant the old-fashioned way with the cross multiplication, and here we get 6, which is equal to the product of our scalings. Now, right now we're just trying to build intuition, but it shouldn't be a shock that we found 2 scalings here for a 2-dimensional system, because what we have here are 2 vectors, and with those 2 vectors and how they're scaled, can we also explain the transformations of the other 2 elements? And the answer is absolutely. Even though this is not a diagonal matrix, this information by itself for a 2x2 matrix is sufficient to define A. If you knew just this, there's only one matrix that'll do just this. So again, is knowing these effects enough to completely capture? Yes. Let's take a look at how that can be shown in the next page. If we know the scaling effect for each, here's the key thing, vector in a basis for the input space, that completely captures everything we need to know about the transformational effect of that matrix. Let's do this in the general case. So we're going to have a linear transform that goes from V to V, and this is very clearly an n-dimensional space. How do we know? Because we have a basis with n vectors in it, and the number of vectors in a basis is the dimension of the space, all that stuff. And if we know exactly the information we saw on the last page, if we know that transforming one vector gives us the same vector back, and for historical reasons, I'm not sure why, we use lambda a lot of the time. Sometimes you'll see R in other texts. We're going to stick with lambda here, the scaling factor. If we can express mathematically what we just expressed in words over here, some vector, when you multiply it by a, is giving the same vector back, just scaled by 3. That's this version here in mathematics. Then what we can do is prove that if we have just that information, so just knowing some vectors are scaled, but it's enough of them to make a basis, then we can transform any vector at all in the input space. And again, this is a complicated expression up here. It'd be an n by n matrix, could be full of numbers, who knows. As long as we can find some building blocks that are simply scaled, then we have all the information we need to reconstruct that. All right, so let's do this proof. Because the set v1 to vn is a basis, then for any basic vector in V, pick any random vector, any arbitrary vector in V, there exist coefficients such that that V can be expressed in terms of this basis. That's the whole point of a basis. Think of your xy axes. We can express any vector in terms of the x and y unit vectors. So we can always express this as a1 v1 plus all the way up to an vn. So exist the coefficients a1 through an for each of the basis vectors. If that's the case, then the transform of that vector v, and this is what we're trying to find, right? I want to know, can I transform v? Can I get a formula for that if I only know the building block ones here? And the answer is yes, because we can replace v with all this stuff. a1 v1 vector plus an vn is a vector. My v is this breakdown into the components along the basis vectors. That's our decomposition of v along the bases, along the basis. Then we have the linearity. So if I have sums of vectors, but L is linear, then if I have scalar products, I can expand them out. I get this. And notice the change in the ordering is crucial here. I had multipliers, but they're out front now. I had sums, but now they're outside as well. What we now have are the transforms of just the basis vectors. What's the L of v1? What's the L of vn? Well, that's the only thing we actually know about our transform, is how those vectors get transformed, and they get simply scaled by a constant. So this is by linearity of L. And then the A1 stays. What's the transform? What's this complicated transform of V1? Well, it's going to be lambda 1, V1. What's the transform of Vn? It could be complicated, but we picked it so it wasn't. Lambda Vn. So this is by our info about the little things that we know about L, that it transforms some vectors by scaling them. We get this combination here, which is fully defined. We know all the A's. Those are the coefficients. How many of the basis vectors do I need to make up V? And we know the lambdas because that's what we know about our transform. And so, knowing this information about a 2x2 system, that this vector gets scaled by 3 and this other vector gets scaled by 2, and those are a basis, that's enough to completely define our A matrix. And that works in 5 dimensions, 1,000 dimensions, it doesn't matter. If we know a set of vectors that are simply scaled by the transform, not shifted, not transformed, let's go back for a second, not turned into something else like these two vectors here were. If we can find the vectors that are just scaled, and we can find enough of them to make a basis, then we have all the information we need to define our matrix. And it's simpler, right? Imagine, well, even just this 2x2 matrix. This looks ugly. How do I look at that and know what's happening? If I write out in words, hey, this matrix scales this vector by 3, anything in this direction by 2, no, I get that. That's a nice summary compared to the matrix notation here. And it's what we just discovered is that those two forms are perfectly interchangeable.